Thank you all so much for coming tonight. We are very pleased to have Dan back. He came, I think, at the end of last year to do a presentation, Clouds, Chemistry, and Climate Change. Tonight, he's going to teach everyone how to be an effective climate citizen. I want to particularly thank Yvonne Stapp. She coordinates all of these awesome science literacy programs here at the library. She is very knowledgeable about what we need to know about, so we're happy to be collaborating with her. I'm going to hand it over to Yvonne now.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to our first talk in a very special series on citizen literacy. The series is a joint effort by Science for the Public, Belmont Public Library, and Belmont Media Center, and the purpose is to provide really good information and resources and opportunities to talk with experts on important science, media, and civic concerns. So you'll be hearing more about this. It'll be announced on the library webpage and so forth too. The work is a work in progress, and your input as concerned citizens is really important. So this is a great opportunity, and we certainly need this input at this time. We start off tonight with a discussion on climate change, one of the most important issues of our time. And our expert by special request is Professor Dan Cziczo of MIT. And in this talk, he'll first offer the important facts about climate change, followed by the most effective ways for citizens to affect policy on the large scale and the most effective things we can do to mitigate climate change in our everyday lives. There will be plenty of time for questions and discussion. Dan Cziczo is Associate Professor of Atmospheric Chemistry at MIT, where he also serves in the Civil and Environmental Engineering group. He's an expert on the relationship between clouds and climate. Dr. Cziczo has been involved in major atmospheric missions for NASA, and maybe he'll tell us about that at some point. And he's received numerous awards. He's a wonderful translator of technical information, which was why I was ordered to get Dan back here, okay? Because he's such a good translator of this stuff. And we are very honored to welcome him back to Belmont tonight. Welcome, sir.
Thank you very much. Thank you. So I wanted to start out by saying thank you for having me back. So it was a real pleasure to come out last fall and get a chance to talk about some of the science of climate change. What I'd like to do today is switch gears a little bit. Instead of just talking about the science, we'll start out with that. So as Yvonne mentioned, I'd like to give you some of the background, some of the facts. But then we'll move on to policy, a little bit about sort of the history of climate policy. Think of this as a quick, brief history lesson of the last 20 or so years. And then we'll move on to actions, which is, I think, something that a lot of folks are interested in nowadays. What can we do as citizens, and where are we moving forward? And there's a number of answers to that. Along the way, I hope you have fun with what we talk about. I'll be happy to take questions at the end. And what I'll do, I think Yvonne mentioned last time, is to go ahead and repeat those so that the folks in the audience can hear, and then we'll go from there. But if anything's unclear, jot a note down, remember to ask at the end, and I'm happy to stick around afterwards and we can talk about it. In addition to saying thank you guys for having me back, I have a few other thank yous to do before we get started. These are the folks in my group at MIT. They're the ones that really make this worth doing. So, I have the privilege of working with some incredible young folks, all the way from high school to graduate school to postdoctoral fellows, and they're the ones that do all of the hard work. I'm going to do one shameless plug, but it has a reason. I get a chance to teach a summer school on climate change from science to solutions. And the reason that I wanted to mention that is that I've mined some of that for some of the stuff that we'll talk about today. So I co-teach that with Noel Saline. There's a number of people that we have in for guest lectures. You guys would be welcome to sign up next year. It occurs for about a 5-day period over the summer, but it's really taught me a great deal. So one thing that Noel and I decided early on was that we weren't going to possibly know everything, so we were going to try to bring experts in from outside to teach us what we needed to know, and therefore the students. And so I'll try to mention where I'm stealing data from those folks as we go through and try to give proper credit to that. So the first thing to talk about really is the science of climate change. Why is it that we're worried about climate change? There's a lot of misconceptions out in the media. You watch one channel and you hear that the sky is falling, you listen to another channel and there's nothing at all wrong. So, we as adults need to make educated decisions about this. And so what are those educated decisions and what are they based on? And so Yvonne knows that this is one of my favorite quotes. It's from George Santayana, and it's, "Those who cannot remember the past are condemned to repeat it." And the reason I like to put this up about climate change is that if we don't understand the climate history of the planet, we're going to be condemned to repeat it. And so this is a climate history of the planet going back about 1 million years in time. And on the Y up there, you can see the temperature of the planet, and then years before present. So you can think about this as being, today. This got built a few years ago, but on this time scale, it's completely irrelevant. Everything that's happening in our lifetime is probably happening under my fingernail right there. So you go back in time, and the first thing that you notice is that there's these huge swings in the temperature of the planet. That's 4 degrees, plus or minus, and that's degrees C. So degrees C is a little bit more than a degree Fahrenheit. And so you can see that there's times that have been much colder for the planet and times that have been actually a little bit warmer than present. So those colder periods are what we term as ice ages. The periods that are warmer, the period that we're in right now, are called interstitial periods between ice ages. And so most people will tell you, well, the climate of the planet has changed over time, so we don't have to worry about it. It's completely natural. That has some truth to it. Humankind was not around changing the atmosphere for most of this record, and yet you can see that climate has swung back and forth. There's another thing that you'll notice, though, about those changes is that it's sort of periodic. It's almost like, looking at a metronome or something like that. You can see that there's almost a rhythm to this. And so the first person that figured this out was a scientist in the 1920s named Milankovitch. And so what Milankovitch realized was that there is some periodicity to the Earth's climate. There's some repetition, and it really has to do with orbital mechanics. It has to do with how our planet moves around the sun. Is it a little bit further away? Is it a little bit closer? It precesses like a top. Where is that top? Does it point towards the sun during summer or away? And that's constantly changing. And all of those different factors are changing slowly over tens of thousands of years with respect to each other as well. And so what Milankovitch did was he sort of added all of these things up. And you can imagine this is an age before computers. So he's doing this all with pencil and paper. And he realized that what you would do is you would add up all of those different factors, and then you would come up with sort of a sum of all of those things. And when you had more energy, insolation coming into the planet would be warmer. It would be in one of those interstitial periods. If there was a little bit less energy, you would be in one of those ice age periods. And the climate of the planet tracks this really well. So his predictions on paper matched up with our understanding of the history of the planet. So this is all well and good. And if that was all to the talk, I would say all climate was natural and we don't have anything to worry about, and you guys can all go home and it's only a quarter after the hour. There's more to it than that, so please hold on to your seats. So the reason that we are all concerned about this is what happens if we zoom in on just the last chunk? So instead of that 1 million years, what if we just look at the last few thousand years? You can think of this as really the rise of civilization, right? I mean, the ancient Egyptians, the Romans were past this 2,000 years, but you sort of think about modern history, and it's really in this time frame here. And the first thing that you'll notice is that temperature bar on the left-hand side is no longer plus and minus 4. We don't have big swings in climate over the last couple of thousand years. We have swings of a tenth or a few tenths of a degree. And that's actually a little bit remarkable because when we go back in history, we think about big changes in climate, like volcanoes going out and blotting out the sun. And these are very small on this scale. They're not like ice ages. They're not like interstitial periods. They're like tenths of a degree. There's other things like the medieval warm period, the little ice age, again, tenths of a degree shift. There's one more thing that you should see on this figure right here, which is there's this rise in temperature that's been going on only over about the last 100 years, since the Industrial Revolution. That's a signal that wasn't predicted by Milankovitch. It's a signal that there's nothing that has to do with orbital mechanics. It's not the sun being slightly warmer, or the Earth tilting in some way. This is a very rapid temperature signal, and it correlates with human activities. And we'll talk more about what those human activities are in the next few minutes. But there is one point that I'd like to hammer home, which is if you think about human civilization, it's not a coincidence that it's happened during a period of very steady climate. Humans didn't evolve civilization as we abruptly went from an ice age to an interstitial period, or an interstitial period to an ice age. Humans in some anatomically modern form have been around for a long time, a good part of that million-year record that I showed you earlier. But we only evolved a civilization in the last few thousand years during what just happens to be almost the most stable period of climate that we've seen in that time. So just remember that those two things are very likely not a coincidence, that our ability to adapt to the world around us is really because it has been in a stable climate phase. But that appears to not be the case anymore. Something else is going on. So what is that something else? One of the things that I've talked to Yvonne a great deal about, and she was very kind to mention some of the work that we've done at MIT, I'm an experimentalist. I like to get my hands dirty. I like to make measurements and build instruments. And so my group is sort of set up around that. And I'm also sort of a history buff, and I like learning about where it is that we came from where measurements were made 100 years ago. And so this is one of the guys that's responsible for that, and one of my sort of scientific heroes. This is John Tyndall, who was a Brit. And he was really interested in what it was about the Earth's atmosphere that made the planet as warm as it was. And so he was another experimentalist. He built this instrument right here. It's called a comparative spectrometer. That was a fancy way of saying that he would fill this tube right here with different substances, different gases from the Earth's atmosphere. He'd pass different types of energy. You can imagine one of them being sunlight through them. And he wanted to see how they would interact. And so one of the things that Tyndall did was he put material in there. At the time, they knew that the Earth's atmosphere was largely nitrogen and oxygen. He put it into this comparative spectrometer. He passed sunlight through, and it didn't do anything. He passed the heat of the planet, the thermal heat of the planet through it, and it didn't do anything. It didn't absorb it. It didn't change it in any way. And he sort of scratched his head. And then he started going to some of the more trace components in the atmosphere. And he was really the first one that figured out that carbon dioxide in the atmosphere was responsible for catching some of the heat that was trying to come off of the planet, trapping it, and then re-radiating it back towards the planet. The carbon dioxide wasn't actually making heat. It wasn't making energy. It was acting like a blanket. It was essentially covering the planet, trapping some of that heat, and allowing that heat to go back to the planet to keep it warm. It's the same thing as us in a blanket. Blanket doesn't create heat, I guess, unless it's an electric blanket, but think of a regular blanket. And you throw it over yourself. What is it actually doing? It's just trying to keep some of your heat closer to your body instead of escaping to the room. And that's why we cover up during the night or during the winter time or something like that. Carbon dioxide was doing the same thing. And Tyndall figured this out, and he figured out some of the other components that were doing that as well in the Earth's atmosphere, some of the minor components. I should give a quick shout out to Eunice Foote as well. Eunice Foote was actually from Cambridge, Massachusetts. She was working at the same time. This was the mid to late 1800s. There was a rule in place that said that women could not present at scientific conferences. And so Eunice had to pick somebody to present her work. And apparently the only thing that she didn't do well was pick people to present her work at scientific conferences. Something that you would never worry about nowadays. And so she was unfortunately largely forgotten until recently. There was a really nice article in the New York Times, I guess a couple years ago now, that sort of talked about her and her abilities and what she did. And she was really a contemporary of Tyndall. And now we start to realize that they were really working on the same problem at the same time, doing almost exactly equivalent work, and she yet didn't get credit for it. A good lesson to us all moving into the future. So you can't just be an experimentalist, you also have to be a theoretician. And so Tyndall sort of did the basic work of understanding what was possibly happening in the Earth's atmosphere, why it was keeping warm, and why it might be changing over time, especially an effect that humans could have. But the person that put the pieces together was this guy. He was a Swede, Irenaeus. And Svante picked up this idea that there was this substance, carbon dioxide, that was completely natural when Tyndall was working. He was working very early in the Industrial Revolution. But there was this substance in the Earth's atmosphere that could affect the heat trapping capacity, how warm the planet was. And so Tyndall was really interested in this substance and what would happen if you changed the amount. And so he wrote this paper in the late 1800s where he talked about changing the amount of carbonic acid, the way that they discussed CO2, carbon dioxide back then. And if you did this, that it would increase the temperature of the planet. He's the first one that we talk about as coming up with an idea of climate sensitivity. So climate sensitivity is this idea that if you take the amount of CO2 in the atmosphere and you double it, what effect does it have on temperature? And so he worked this out, and he said it was if you doubled the amount of CO2 from before the Industrial Revolution and looked at the temperature of the planet, that we would warm the planet 5.5 degrees C. He made a math mistake, and so he published a second paper and revised his estimate downward to about 4 degrees C, the first two estimates of climate sensitivity. I always tell my students that this is not a good way to work, that you make a mistake and then publish a second paper. So I always tell them, make sure that you do it right and get one good paper instead of two that people have to cite. But nonetheless, Svante caught his mistake and did this. The interesting thing about this is that he didn't do it for the reason that you would think. Most people would say, oh, Svante Arrhenius, he was way ahead of his time. He was worried about carbon dioxide from the Industrial Revolution, from burning oil and burning coal, and worried about warming up the planet. That's not true at all. Svante was from Sweden. He actually writes in his papers about how much he hates Scandinavia, how cold it is, and how long the winters are. He wanted to light the coal fields of Northern Europe on fire to warm the planet up so that he could make it nicer for him in Scandinavia. And he also was thinking about moving the grain belt north in Europe from, Germany into Scandinavia, and this is going to be great for the Scandinavians. I don't think I've ever seen him worry about Southern Europe and the effect that it would have down there. He was very much a homer in that respect. But he was already thinking about this ability to change the climate of the planet by putting something into the atmosphere, namely CO2. So what's happened since Svante and Tyndall were around? Well, this goes just back to the 1970s. But what you can see is that these are the greenhouse gases, the things that Tyndall found to be important and that Svante did his theoretical studies on. So mostly CO2 from fossil fuel, but other industrial, other human emissions. And you can see that they're increasing year after year. So this is the amount that's in the atmosphere. It's also the amount being emitted every year is increasing. And so what result is that going to have on the planet? Well, the planet is now warmer than it was before. It's just like that graph that I showed you early on with the little blue trace that was increasing since the late 1800s. That has continued and it's accelerated over the last few decades. And so this is the temperature of the planet, the difference between 2012 and 1900, so over 110, 112 year period. And you can see almost every one of the blocks around the planet, and these are measurements, are warmer now than they were before. The white parts are usually lack of data, lack of stations. There are a few places that are a little bit cooler, and we think that we understand that. The one off of Greenland up there is probably melting of the Greenland ice sheet and cold fresh water being put into the ocean. There's also the thought that some of this has to do with an increase in particles in the atmosphere, and I'll talk about these in a few moments. Same thing over the southeastern US. If you look at the planet on average for an entire year, and we think about what the temperature is, then you can list the warmest years on record. So the warmest year on record was 2016, 2015, 2014, 2010. This is going back into the 1800s. Does anybody see anything on there outside of their lifetime? No. So when people ask me about, well, is climate change going to be different for the next generation? My response is climate change is different for this generation. The climate that I was born into is not the climate that we have on the planet now. The planet is already a degree C or so, 1.5 degrees Fahrenheit warmer than it was when I was born. I grew up in Chicago. They talked about the frozen tundra of Green Bay for football season. The temperature in Green Bay now on average is about what it was in Chicago when I was born. The temperature in Chicago now is about what it was in southern Illinois when I was born. You can do the same type of thing. Boston is much more like what New York used to be in the early 1970s, early to mid 1970s and so on. New York is much more like Maryland and so on. Just step yourself down. That's the kind of change we've undergone. So how is SFONT doing? Well, if you double CO2, we've gone up by about 50%. SFONT would say a doubling is about 4 degrees C, but we're only up about 1.5 degrees. So he's only about half right. His estimate is appearing to be a little bit low. The temperature hasn't warmed as much as he suggested. The question is, well, why is that? And this is our specialty on climate. I will let you guys answer that. This is a real picture of the Earth. It's actually a mosaic image from the Japanese Space Agency. They took a set of really perfect images of the Earth. They knit them together to make this beautiful poster. And it's actually something that I had on the wall when I was a kid. But what did they intentionally not take pictures of? Clouds. Clouds and particles. So at any one time, the Earth, if you took a real picture of it, instead of cherry-picking different spots on it, should look like this. It should be covered with clouds. Those clouds and the particles in it are very reflective. They reflect some sunlight back into space. Just like that CO2 is a blanket, the clouds around the planet are like sunshades. They reflect some energy back into space before it can make it down to the surface of the planet. And so what I'm trying to tell you, or what I'm trying to say, is that we as humans are changing the particles in the atmosphere, which means we're changing the clouds. They're the condensation sites for droplets and for ice crystals at the same time. We probably have slightly more clouds than we did before human activities took hold. And so we've got this balancing act going on. We're warming the climate with the addition of greenhouse gases. We're putting more blankets over somebody. But at the same time, we're slightly changing the sunshade over their head. And the balancing act between those two things is that the greenhouse gases are winning. The planet is warmer as a result, but it's not quite as warm as it could have been if we weren't also doing something about the particulates in the atmosphere. And so if you don't believe me about particles changing, think to that dirty truck in front of you as you were commuting to work this morning. You know, or that power plant or that factory down the street that's got a smokestack and is spewing out particles. You can also think about this. This is Singapore a few years ago, and this is a pall of smoke that's sitting over Singapore. So you can say, well, smoke's a natural particle. That was here before people. Not true. This is smoke from land clearing. So this is folks around Singapore that are burning peat bogs and trees and vegetation to clear it so that they can do some planting. So this is smoke that's there because of human activities, and it's made this pall over the city. And so what you can see is that this should have otherwise been a bright blue day, but that sunlight isn't able to make it down to the surface because it strikes that smoke, and it gets reflected in all kinds of different directions. So the camera here is seeing this diffuse light because of that smoke reflecting the sunlight away. And some of it's making it back into space. Sunlight that would have otherwise warmed the planet more than it did if it wasn't there. We call this, by the way, the direct effect of particles on climate. That implies that there's also something called the indirect effect of particles on climate, and that's because particles also act as these condensation sites for clouds, the site that droplets and ice crystals form on. Mostly we think of clouds as being ice clouds now because it's wintertime, but I guess it was raining pretty heavily over the weekend. At the heart of every one of those droplets or ice crystals is a small particle. And as we change, as we augment the amount of particles in the atmosphere, we get more clouds, more droplets, and more ice as a result. So more clouds is one factor. The other factor is that you can think of the cloud on the left there as being sort of a pre-industrial, pre-human cloud. On the right is the post-human cloud. What I mean by that is that there's less particles on the left than there are on the right, but there's the same amount of water in the atmosphere between them. So if there's more particles, more condensation sites, you end up with smaller droplets as a result. Smaller droplets tend to be more reflective. It's a whiter cloud, brighter, more radiating. It'll send more sunlight back into space. These smaller droplets also don't fall out as fast. They don't rain as fast. And so that cloud hangs around longer. And so there's a secondary effect here, which is that there's also a change in precipitation. There's probably slightly different precipitation patterns from before human activities to post-human activities. These are the things in climate that I'm really interested in. They're the things that we work on quite a bit. You probably haven't heard about them on the news. It's sort of the cutting edge thing that we're trying to do to understand uncertainty in climate change. I often joke that I call it job security, because as long as people don't know, it gives me something to do in the laboratory. Okay, so let's add it all up. Greenhouse gases, big positive warming, some uncertainty on it. Other anthropogenic forcing, anthropogenic is just a fancy term for human forcing. Negative, so these are the particles and the clouds that are spawning, also a big uncertainty. But you add these two things up, and what do you end up getting? You end up with a little bit less of a positive forcing, a little bit less of a warming as a result of the extra particles in clouds. And it turns out that the observations and what we understand of the changes in our atmosphere are almost identical. We're doing a pretty good job about this. This is important to mention because you'll often hear that we don't know anything about climate, that we don't know what's going to happen, that there's this huge uncertainty. There certainly is uncertainty. It could be small. It could be somewhat warmer than we think, than our best guess is. It could be somewhat cooler than that. But we're actually doing a pretty good job. And what we're working on now is trying to shrink these uncertainty bars as much as we can. So that's sort of the first take-home message, is that there's this interplay between greenhouse gases, particles, and clouds. The greenhouse gases, predominantly CO2, are winning. So we're ending up with a warmer climate. Exactly how much warmer is still debatable. It's still dependent on that uncertainty. We've got a pretty good handle on it. I can tell you it's going to be a good bit warmer in 10 years, 50 years, and so on. But exactly how much is it going to be 3.1 or 3.2 degrees warmer? That's something that I can't tell you. But I can tell you it's going to be 3 plus or minus a half. I think that's pretty good at this point. Please.
The baseline for the natural cycle is shown as 0. Is that the baseline in the absence of these other effects that the fellow's name was predicted?
The natural forcings on the bottom. Yeah.
But you've normalized it.
It's a good question. So I'll repeat that for the crowd just so that you guys can hear in the back. So the question was, what is the baseline for the natural forcings and natural internal variability? So what that is referring to is how much has the natural system changed over the time of this measurement. So this measurement is from 1950 to 2010. So the implication here is not that the natural system doesn't change over time. It's just that it does so rather slowly over this amount of time. The sun is not a lot warmer than it was in 1950. The Earth's orbital mechanics are not significantly different than in 1950. If we extended that time back to the last ice age, that could be very large. It could swamp all of this. But since 1950, there's almost no change in that. And we have measured that, and we know that quite well. So there's measurements over that whole period of time. Hope that makes sense. Okay, so that is the history. That's the basic science. And one of the things that I enjoy about giving these types of lectures is that I think that this is rather complicated, right? I mean, we all took science, and we took biology, we took physics when we were in high school. But a lot of times, folks haven't taken it since that time. And yet there's these complex problems, especially climate science, since then. And so sometimes we have to sort of reset ourselves, and we have to think about this problem and the complexities of it, sort of go through the basic science of it before we can start making informed decisions. And so hopefully in the last 20-some minutes, we've been able to do that, and we've talked about the basics. And again, I would invite you, if anything doesn't make sense, grab me afterwards or ask questions. So the next two parts of this are the policy aspect and then what we can do as sort of interested citizens in this. And so the policy is thanks to my co-teacher for the summer school, Noelle Saline. And one of Noelle's specialties is understanding policy. She's been working a lot in environmental pollutants recently, and we can think of carbon dioxide as being essentially one of those pollutants. So what is the sort of history behind this? Well, again, a lot of times if you listen to the news media, you might get this sort of thought that we've only been doing this for a couple of years. People have heard probably about the Paris Accord, and they might think that that was really where climate change started. That's not true at all. So we have been talking about the possible human effects on climate from greenhouse gases in a policy sense since at least the 1990s. It turns out that there are government reports, presidential reports going back to the Johnson administration, the 1960s, talking about greenhouse gases, the effect on climate, and mitigation steps, things that we could possibly do to offset some of that warming or to mask some of that warming. 1960s, that is not probably something that you're going to hear about climate on the nightly news, but that's how long we've been thinking about this. There's a whole host of things that have gone on since that point in time. In the late 1980s, the IPCC was formed. That's the Intergovernmental Panel on Climate Change. So IPCC was this idea as people were just starting to think about the impact that climate might have on us because of warming, because of addition of greenhouse gases. How could we assess this? How could we start to get a handle on it? So way back then, people grabbed together as many scientists as they could. It now numbers in the many thousands of scientists. And they were essentially tasked with writing a report every 4 to 5 years. These were called assessment reports, ARs. And those scientists would get together. They would say, what is the data telling us? What is our certainty on it? And how can we project that into the future? And then every few years, they would get together and say, do we know more? Do we have more data? Do we understand this better? Can we say something more definitive than we did last time? We would be really bad at our job if we couldn't do better than we did a generation ago. Well, the first report came out in 1990. So this was climate change, the first basic report from the IPCC. This is the last one. This is AR5, which came out a few years ago, 2013. We're about due for AR6. They're working on it right now. If you look on the one on the left, and I'm old enough to remember when this was coming out, and I had a copy of it when I was a graduate student to read, the idea is pretty vague. You know, they talk about, well, we think we understand the physics behind it. You know, a lot of it referred back to things like what Svante was doing. But it was essentially saying that the increase will enhance the greenhouse effect, resulting in a warming of the surface. That's pretty wishy-washy, right? It's not saying it's going to be this much warmer, we really have to worry about it, what's going on. But you know, this was pretty early on. That blue trace, that temperature increase really hadn't started out. We were sort of still in the noise. Well, what's happened in the intervening years? Well, this is that increase in greenhouse gases that I showed you on that figure. And now we're sort of 1.5 degrees warmer than we were in 1990, in the late 80s. And so now we can say that warming of the climate system is unequivocal. You would not believe the amount of discussion that it took to get to that word, unequivocal. It can't be argued with that the climate system is warmer now than it used to be. This was not something they were comfortable saying in the 1990s. In the 1990s, it might have been variability. Unequivocal. It is extremely likely that term came with a percentage, 95% certain, that human influence has been the dominant cause of the observed warming since the mid-20th century. Scientists hate to say 100%, so they were comfortable getting to 95%. But one of the things I would ask you is if there was a vote and it was 5% to 95%, which of those things would you end up thinking was the true thing, right? Another way to think about it too is in terms of insurance. If I told you that something was 95% probable, you would probably take out insurance to guard against whatever that was. If it was 5%, you might still do that. But certainly in this case, if we're saying that there's a 95% chance that something we're doing is having this effect, you're probably going to go down one sort of path of reasoning. And that's what the IPCC was really trying to get at with this. I want to acknowledge a few things as we talk about this, though. The world has very much changed in that intervening couple of decades since 1990. So if you sort of think about this as being, 30 some odd years in time, what's changed? Well, if you think about how the developed world behaves versus the developing world, there's been a state change. The dominant source of CO2, the dominant source of the greenhouse gases, when these reports started in the 1990s, were developed countries. The United States, Western Europe, at that point in time, the Soviet Union. Well, what about now? You can see that the areas of growth on that curve at the latter part of it are really developing countries, China, India. Those are now the large emitters of CO2 and the other greenhouse gases. That doesn't mean that there isn't a historical responsibility for what was put in the atmosphere before, or that we're not per capita still putting in the most CO2. But it is something that we need to pay attention to, is that this is not a single country problem. There's many countries that are involved in this. Another thing to think about is that we've developed on the backbone of fossil fuels. Our country was developed on coal and oil. Same thing for Western Europe. can we really say that other countries are not going to be allowed to also develop their economy? These are just things that I want you guys to think about, but this is a real issue. How do you say, well, I'm sorry, we already burned all of the carbon that can be burned, and so now you're going to have to figure out another way to do it? That's one of the issues that there is with developing countries. They feel like now it's their chance to do this as well. So where are we now? Well, the last major climate accord, the last major step in sort of intergovernmental policy was Paris, and this is now a couple of years old. This was towards the end of 2015, and as we all know, a lot has changed since the end of 2015. But what did Paris try to do? Well, Paris tried to look at the temperature of the planet, and they said, well, what are we really going after? It's probably not an amount of CO2 in the atmosphere. It's probably not behavior so much. It's that we need to have a target. What is it that we can't really live with? And so for what I am willing to admit are fairly arbitrary reasons, they came up with this idea of 2 degrees of warming over pre-industrial levels. So I've already said that, you know, in degrees C now, we're already about halfway towards that. We're already about a degree warmer than we were in pre-industrial time. And they had some reasons for picking out 2 degrees. One, it's a nice round number. But there are other reasons behind it, and a lot of these had to do with adaptation, mitigation, sea level rise, and they felt that it was a good round number that sort of encapsulated all of those things. And so what they wanted to do was see if they could put in place policies that allowed for 2 degrees to be the possible rise of the planet. I want to give you guys some perspective on that. If we continue business as usual, where are we going to end up? We're going to end up at 4.5 degrees by the year 2100. That's more than 2 degrees, by the way, right? I mean, all of us had enough math to figure that one out. 3.5 degrees is actually as good as we've done with the current sort of proposals that are on the table for what we're going to do as a world. So we haven't really hit this 2-degree threshold. We've set the goal, and that was one of the important things about Paris. It gave us a target. It gave us something to shoot for. But I just want to be a realist about this and say that we are not meeting those goals yet. Our promises aren't, and certainly our actions, the yellow line on there, are not meeting that. There's some hope that as technology comes online, and we'll talk more about these in a few moments, that we'll be able to bring the carbon down, the carbon dioxide down to try to hit that. But I just want to give you some perspective on this. So where are we as a country? Well, this is good news and this is bad news. During the Obama administration, when Paris was brought out, when it was ratified, the U.S. came out with a plan. So the plan looked something like this: 32% reduction by 2030, electric generation about 40% of U.S. emissions down. So this was approaching that 3.5 degree number, not the 2 degree number, but something better than business as usual, that we were going to drop that down. And then we had a little hiccup in the way. And so this was where the current president came in and said that we're getting out. There has been a lot said, and this is not to be a political discussion. There's a lot of denial that has gone on, saying that this is not happening. I hope one thing that I've done tonight is tried to lay out the scientific framework for what we know and what we don't know, how well we know it, how well we don't know it. That's just science. That's physics, that's math, that's chemistry. Denial, saying that this is not happening, is sticking your head in the sand. It is happening. There is no doubt. We can go back to that unequivocal word. Nonetheless, as a country, there was a decision made that we pulled out of Paris, which means that we are not going to try to meet those commitments. However, and here's hopefully the good news, is that this doesn't seem to be where most of the country's at. So again, depending on where you get your news, you may get different thoughts on this, but right now, something on the order of about 70% of Americans, and it's always hovered in the 60s, 6 out of 10 to 7 out of 10 Americans think that global warming is happening. They're not sticking their head in the sand. So this sort of denial movement you can think of as being a minority of Americans, maybe a little bit less than a third. So how does this break down? Well, just saying that I believe in it or I don't believe in it isn't great. There is a spectrum here. And so the hardcore sort of dismissive folks in this that don't want to hear that science, that don't believe in it, are really sort of on the order of 1 in 10. There's another 1 in 10 that are doubtful of this but are not ruling it out. And then you sort of have something on the order of, disengaged, they don't want to hear it, another 1 in 10. And so this is really that 30% that we talked about. Anywhere from cautious to alarmed, really alarmed about climate change, is in that 70% number. And I would highlight the concerned as probably something that, that's probably a good word to use for this, anywhere from alarmed to concerned, depending on how you think about it. But you can see that sort of solidly the majority, 70% of Americans, sort of fit in that category. So it's not quite as dire as you would think. What have we been trying to do since pulling out of Paris? Well, you have to remember that not all policy is made at the federal level. And so California is always sort of the poster child for this. But when you think of air quality and the movement of air quality in the United States towards better air quality, that has been done at the state level, in particular California. You think about the smog. I lived in LA in the early to mid 90s. It was a horrendous place. I mean, there were times that you couldn't see sort of a mile because of the smog. That has largely been cleaned up. And that wasn't sort of federal, that wasn't EPA, that was California saying, we can't have this anymore. What do we have to do about it? And so this is state level action on climate. It's probably not a map that's that surprising. You sort of look at the West Coast, you look at some of the more progressive central states, you sort of look at the upper Midwest, and then of course where we are in the New England states. And these are the places that are going to be leading the way. Luckily, almost without exception, these are really where a lot of the population is. There's obviously 2 southern states that have a lot of population that are not on there, but I'll try to show you in a moment that the situation isn't quite as dire there as you would think either. This is one of them. So this is Florida. And again, no pun intended, if you're in Florida, you can't stick your head in the sand about climate change, because this is only up to 2016, but it shows you this change over a period of years in the mindset of Floridians, right? I suspect, I don't have the data on this, but I bet that's even more pronounced now after the hurricane season last year. Because one of the things that we've been able to show is that hurricanes pick up more steam. They're somewhat stronger because of global warming, because ocean surface temperatures are warmer, the fuel that feeds hurricanes. So Kerry Emanuel at MIT is one of the experts behind this. I will not do it justice, but I would encourage you to see him talk if you have a chance. He can tell you this. So this is not to say that there's going to be 10 times as many hurricanes in the future because of global warming. That's not true. But the storms that we have are going to be somewhat more powerful. So 4s become 5s, 3s become 4s, and so on. That's the thing that we have to worry about. That's the thing that Floridians are worried about. And so you start seeing these changes going on over periods of time. And it might be a slow change, but it is a steady change in the direction. And so again, just to sort of back this up with a little bit more data, this is sort of, how this belief changes across the US. The average here would be white, the places that don't believe it versus the places that do believe it. Again, the places that believe it more are, of course, the New England states where we live, the Pacific Northwest, and so on. One of the things that I will tell you, though, is that, again, I come from this area right here, and it's hitting average. There's a lot of folks that we've had a chance to work with in the farming community. Farmers we think of as being fairly conservative folks, right? That's not true when it comes to climate change. The folks in the Midwest are already changing their planting strategies. They plant somewhat earlier because it's warmer earlier. They harvest at a different time because the plants are ripe earlier as a result. They've changed the seeds that they plant. They changed the types of corn that they plant in the Midwest. They go to warmer weather varietals. There's also talk in places like the upper Midwest of changing things, for example, from wheat to corn, because it's going to be more viable. Ottavio and I have talked about wine in the past. My family is in Italy. They've already seen the change in harvest season, historical records. So they harvest 3 weeks earlier. They do the trimming of the vines 3 weeks earlier. Everything has moved up in time. In the Pacific Northwest, they're starting to plant different varietals that used to only be possible further south. There's groups that are making huge bets by planting grapes in British Columbia, things that used to only grow in Oregon and southern Washington state as a result. So even groups that we think of as being conservative are hedging their bets, and they're starting to do things based upon projections of climate change. In transitioning to the last part, which is sort of the what can we do about this, or the things that you all should be paying attention to, hopefully, is that, in making that transition, what are the big emitters? Where is it that we are creating as a society, because we all use these products, where are we creating the most carbon? And so you can see at the top of this, oil and gas, electric utilities, and so on. So one of the big things is that transportation is causing a lot of the CO2. So for us, the thing that we can change is personal cars. I drove today so that I could get here. I try to take the bus and the T to get into work. I see people shaking their head. I feel your pain. I mean, I've done this now for years, and there's real problems with that. Nonetheless, this is one of the things that we all have an effect over. More efficient cars are one of the things. People go, oh, great, I can use an electric car. No. If the electricity that's powering your car is coming from oil and gas, an electric car is not a benefit. And so then you have to start thinking about these electrical utilities, which are creating a lot of that. If the electricity for your car is coming from solar panels on the top of your house, now you've got a win. If that electricity is coming from a nuclear power plant, not a popular choice in some circles, and I understand that, but if it's coming from nuclear, if it's coming from renewable, now that's a net win. It's not a carbon atom that you're producing to do that. You can see the other things that are on here, though. In addition to this, steel, construction, that type of thing. Concrete features prominently on here. Building new buildings, building large buildings, building non-green buildings is a substantial amount of the CO2 that we have in the atmosphere. But you can think of the things that we can do about it. These are the things that we can reduce. And so we'll just use that as a quick transition into action items. And Paul Kirschen is one of the guest lecturers that Noelle and I have brought into our class. And I've stolen a few slides from him. He does a great deal of work with coastal resilience in an area of rising seas. And so I just think that this is a nice little quote. All human and natural systems are sensitive to climate. Thus, as climate changes, their services will change. Therefore, we must consider how we will adjust to the changes, the process of adaptation. And so I think that this is really important because it acknowledges that climate change isn't going to happen. It has happened. And it's going to continue to happen, no matter how much we might want to. The coal-fired power plant down the street is not going to turn off today. They may have a permit for the next 50 years. How do we adapt to that? How do we mitigate what the change is that's in place? And that's an important part of what we have to talk about. So one thing is, don't ignore the problem. So if we acknowledge that coal-fired power plant is still going, that's okay. If we start bringing online more and more and more coal-fired power plants with lifetimes of 50 or more years, that is sticking our head in the sand. That's the type of thing that we have to be cognizant of and try to change. The other thing is that we then have to adapt to what is in place. So how can you do this? We live in a great place for thinking about this. We're in a very coastal region, and so it's very real to us what happens. The planet gets warmer. The oceans expand. There's more water in the oceans. You get sea level rise. You get stronger storms. You get larger storm surge. You have to accommodate what's going on. You have to protect, or you have to retreat from it. And you can think of all of these in the sense of a coastal zone, right? The retreat is that, I've got a house right next to the ocean's coming up. I might have to move that house back, or I might have to move that house up. That's what happened in New Orleans after Katrina. You can protect yourself. You can build seawalls. You can build dikes. You can build levees. You can do that type of thing. That's a strategy that's been employed in places like Houston. There's talk, you probably saw this in the Boston Globe after the big storm that we had in early January, about that we might have to think about doing this around the Boston area, that there's plans in place for that. Accommodate really means this idea of, accommodating the change that's already happening. And it sort of folds into the other two. But can we deal with some of that flooding? Can we set aside more land that we understand is going to flood and not try to build on it, not try to develop it, or try to create places where that water, for example, can go? You can think about this all in terms of temperature as well, right? I mean, if you have a higher temperature, can you sort of retreat from the worst temperature areas? There's a lot of studies that suggest parts of the Persian Gulf area will become uninhabitable without air conditioning by that year 2100. and you protect against it? Can you build shelters? Can you build things that are going to allow you to adapt or take care of the heat? Folks that might not have air conditioning at home, older folks, younger folks, people without protection, that type of thing. Or can you just accommodate it? Can you change the plants that you're planting and deal with it that way? I think in the interest of time, I'm going to start to wrap up because I know that we'd like to finish by 8 o'clock, and I'd like to make sure that we have time to do that. I will just mention a few other things as we start to close out. In terms of energy, I'm a realist in the sense that civilization runs on energy. This idea that we can sort of turn off all the power and still have things work is not realistic. I have good friends in Germany where they did turn off their nuclear power. And I said, well, what are you going to do? And they said, we're going to increase efficiency. And I said, okay, but where's the power still going to come from? You're turning off all this power. And they said, we're going to increase efficiency. And do you know what they're doing now that they turned all that nuclear off? They're buying power from Eastern Europe, which is all coal-fired power plants and gas-fired power plants and oil-fired power plants. So they feel better about having gotten rid of their nuclear capability, but their carbon footprint has gone up as a result. And so we have to be realistic about this. Can we do at least partial renewables? Can we acknowledge and start to research and put more nuclear into our portfolio? That's a question. Finally, can we sequester carbon? The temperature of the planet is already a degree or on the order of a degree warmer. We've said that we have this target of 2 degrees, but the business as usual and even the promises we made have us on sort of a 3.5 or even a 5-something degree path. What can we think about doing in terms of pulling some of that carbon dioxide out? Well, it turns out that people smarter than I am have already thought about this. And so this was a report that was written a few years ago by the National Research Council, the National Academy of Sciences in the US. And the idea was, can we try to remove that carbon? Are there different ways that we can do this? And again, in the interest of time, I'd be happy to talk about this later. But there's a number of strategies for trying to do this, to try to draw down that CO2. You know, can you burn fossil fuels, capture that carbon, and drive it back down into the Earth system, into those wells that you pulled gas or something out of? This is called carbon sequestration. There's other ideas like, you know, burning plants, using plants to capture CO2, grow from the CO2 in the atmosphere, perhaps use them for some energy, but then take that carbon, maybe charcoal, and bury it back in the Earth. And so this has been used a lot, this thought process of sequestering carbon. One thing that I wanted to leave you with is that this isn't science fiction. So if you hear carbon sequestration, it's not something that's going to happen in 50 years. It's happening now. So this is a project in Scandinavia. So I guess we've come full circle in a way. We're going back to Scandinavia. This is an extraction site for natural gas. This is natural gas that happens to come out of the Earth with a substantial fraction of CO2 in it. So it's not CO2 that's being burned. It's CO2 that's in that natural gas. In the old days, this is quite common that you get natural gas with a lot of CO2 in it. In the old days, what they would do is they would do a separation of those two things, normally chemically. You would pull out the natural gas that you wanted to burn, and then you would just let the CO2 go back into the atmosphere, thereby increasing it. When this project was put together, the Norwegian government said, no, you're not going to just let that CO2 go. You've got to capture it and sequester it. And so they took it out, and they drive it back into the Earth system, back into the wells, which actually helps improve the extraction of natural gas, but also takes out the CO2 from the system. So this is something that is now being thought of in terms of power plant generation. You've got your coal-fired power plant, your gas-fired power plant. You take that CO2 out and you drive it back into the Earth system. At some point, we really need to think about doing this. If we're going to go on that business as usual trend, there's going to be excess CO2 there that we're going to need to draw out, and it's going to have a penalty. It's easier to do it now when we're burning it than it is sometime in the future when it's floating around as free molecules in the atmosphere. It's much easier at this point than it is to sort of try to pick it out of the atmosphere somewhere over Norway. And so that's why the Norwegians have put this in place. And it's still a viable technology. They're still extracting the gas. It's still economical, and it's still working for them. And so it's just the price that we're willing to pay. So with that, I'm going to say thank you for your guys' time. I'm going to give a quick explanation of my question slide, which is that I had a chance a few months ago to do an article for Popular Science. And so the person came out, and Yvonne has seen me do this before she hosted this, but we have a little experiment where we make a cloud in a jar and we talk about all the particles that are involved and so on. And so I did it for this author at Popular Science. And along the way somewhere, I told him that I was an avid fisherman. And so he apparently sketched this out. And submitted it, and a friend of mine was flying around an airplane. I didn't even know they had written the article, and he came home and he handed it to me and said, "Did you know that you're in Popular Science this month?" And I said, "I had no idea." And it had this cool little cartoon, so I called Kelsey up and got a copy of it, and so now I'm going to use it for my question slide every time from here forward. But I think this is, as a nerdy kid, this was like, everybody's dream is to end up in Popular Science. So I guess I've finally made it in the world. That might be my best award. So with that, thank you again for the invite to come out. I hope this really helped you guys, and please ask any questions you have. Thank you.